Good morning, Year 9. So today's lesson is on relative frequency. We touched a little bit on it yesterday, and those of you that did some of those experiments will have been using relative frequency to work out your probabilities. So if you could start by copying these sentences and fill in the missing words. Okay, should be fairly obvious what the missing words are. Okay, pause if you need to. Okay, other question we've got here is, an ordinary coin is thrown 50 times. Barry says, I'm going to get heads 25 times and tails 25 times. Explain why he could be wrong. Okay, so if it's an ordinary coin, that assumes it's fair. So we would expect to get numbers close to 25 for heads and tails, but we do know that when we do an experiment, okay, things don't come out exactly as the theory tells us. So in theory, we should be getting equal numbers of each, but in practice that often doesn't happen. Okay. So let's have a look. So we've talked about relative frequency. So relative frequency is written as a fraction, just like we did with theoretical probabilities. And relative frequency is the number of successes over the total number of experiments. So one of the experiments you might have done yesterday is the drawing pin experiment. And if you were looking for the relative frequency for pins up, you'd do the number of times you got pins up out of the total number of times you dropped the pin. Okay, or if you were doing the biased dice one, you do the total number of sixes out of the total numbers you've thrown the dice. Okay, so relative frequencies are important because they help us to estimate probabilities when either we can't theoretically get a probability, or we might think that something's biased and we want to check that. Okay. Key thing that you need to understand is that the more experiments that are performed, the better our estimate. Okay, and this is tested a lot on GCSE exams. They often ask for what's the best estimate for the probability, or which relative frequency would you choose, and you must always choose the one that has got the biggest denominator. In other words, the number of experiments is the largest. Okay, so just make sure you've understood that, because that does come up a lot. Okay, let's have a look at an example of a question. Okay, so we've got a bag contains 100 coloured balls. We've got Xavier, Yvonne and Zoe each select a ball from the bag, record if the ball is red and replace the ball, and we've got their results here. So Xavier did that 5 times and picked out 4 red balls. Yvonne did it 20 times and got 16 red balls, and Zoe did it 100 times and got 95 red balls. So Xavier says the probability of choosing a red ball is 4/5. Okay, criticise his statement. All right, so if you remember the last thing I said on the previous page, that we need a lot, the more experiments performed, the better our probability. Well, the problem here is 5 experiments is never going to be enough to get a good estimate. So because he's only carried out 5 trials, this is not enough to make an estimate. Okay, so that's the answer to that one. We're looking for lots of trials. So then part B, Zoe says that the bag must contain 95 red balls. Is she correct? Okay. So we know there were 100 coloured balls in there in total, and we know that Zoe pulled out 95 red balls. Does that mean there were 95 red balls in there to start with? Well, no, it doesn't. Because she may have taken some red balls out more than once, or she might not have taken some out at all. Okay, so we don't know, and unless we tip the container out and physically count how many balls there are, we won't know how many red balls there are. Okay, part 1. Explain why the most accurate estimate of the relative frequency of choosing a red ball is 0.92. So let's have a look up here. Where does 0.92 come from? Because if Xavier's was used, that would give us an estimate of 4/5, which is 0.8. Okay. Yvonne would get 16/20ths. Okay, and if you do that on a calculator, 16/20ths is also 0.8. And Zoe's would be 95 out of 100, which is 0.95. So none of those give me what we're asked to do, which is 0.92. But I just want to come back to that idea again, that the more trials we do, the better our estimate. Well, if you look, we could use all those trials together to get the best estimate. So rather than just use Zoe's or just use Yvonne's or just use Xavier's, we can use the total to get our best estimate. Okay, so if we add up how many red balls were picked out in total, we would have 4 plus 16 plus 95, which is 115 balls in total. Red balls, sorry, were taken out. And if we add up the number of trials, that's 125 trials. Okay, so now I can use that, which is 115 out of 125, and that gives me 0.92. So just coming back to that idea that the more trials that are performed, the better our estimate will be. So use as many trials as you've got evidence for, and here we had 125 trials. So second part of that, does the bag contain 92 red balls? Okay, well, we don't know. Okay, without emptying the bag and counting them, we don't know how many red balls are in there, but 92 would be a good estimate. Okay, so if I had to estimate how many were in there, I would say around 92, but we're never going to know exactly unless we tip the bag out and count them. Okay, so on this next page, I would like you to have a go at these questions here. There's another one at the bottom which I'll scroll down for in a minute. Okay, pause, have a go at those questions, write your answers out. Okay, remember relative frequency is the number of successes out of your total number of trials. Okay. There's question 5, so pause and have a go. Okay, so here are the answers. So question 2, a coin lands on tails 20 times. What's the relative frequency? Well, it's 20 out of 30, but we would cancel that to 2/3. A dice is rolled 50 times and it lands on a 6 37 times. So the relative frequency of a 6 is 37 out of 50. As a decimal, that would be 0.74. Sometimes decimals are easier to sort of understand. Okay, we can see that's close to 1. All right. Robin says the dice is biased towards landing on a 6. Do you think the dice is biased? Explain your answer. So I've put here it's likely to be biased, as the probability of it landing on a 6 should be 1/6. And what we've got is 0.74, which is much higher. Okay. Okay, so what we're getting in our experiment is very different to what we expect. Question 4, we're asked to complete the relative frequency table for heads and tails from this coin experiment. Do we think, so I've got 13 out of 24 heads and 11 over 24 for tails. Do we think the coin is biased? No, the coin doesn't look to be biased. We would expect relative frequencies to be close to 12 out of 24 for a fair coin. Okay, again, we're never going to get exactly 12 out of 24, but both of those numbers are close to 12, so that would suggest it's a fair coin. And number 5, we've rolled a dice 30 times and asked for the relative frequencies, so we should have 2 out of 30, 2 out of 30, 7 out of 30, 3 out of 30, 1 out of 30, and 15 out of 30. So do we think that dice is biased? Yes, because we would expect, because we would expect roughly equal numbers of each number on the dice, and we've got a lot more sixes and very low numbers for 5. Okay, there we go. So get that marked, and hopefully you've understood what relative frequency is about and how we can test for bias and non-bias. Okay, last thing I want to do is just to show again how the probability the more times we do an experiment, the closer the relative frequency becomes to the probability. So we're going to do a simulation. What I need for you to do in your books is to copy the table. I think it goes down to, got down to 130, but if you get down to 100, we'll leave it there. Okay, so you need number of trials going up in tens to 100, and a column for frequency and a column for relative frequency. And then with that, you need a graph. Okay, we are going to, so on your graph, you need numbers going up to 100 on the bottom, which is our number of trials. And up the side, we've got probabilities or relative frequencies. Okay, so we're going up in 0.1s up to 1, which is the highest. Okay, and what we're going to do is we're going to look at the relative frequency of throwing an odd number on a dice. Okay, so pause and get those things into your book. Okay, so once you've got that into your books, we're going to do, we can do this together. We're going to use that dice simulator again that we had before. So I've set it for 1 dice, and we're going to start with doing 10 throws. So I'm going to press 10 here, and we're looking at the frequency of odd numbers. So if I look here, I have got 3, I've got no 1s actually, 3 3s, and 2 5s, so that comes out as 5 is my frequency. So I'm just going to write that in for now, and we'll come back and do the relative frequency in a minute. We'll get these in first. Okay, if I'm going to do another 10, okay, so I've done 20 rolls, so I've got 4 1s and 4 3s, that's 8, 9, 10, 11. Okay, let's do another 10. Okay, so we've got 7 and 5 is 12, and 4 is 16. And so up to number 40, so I'll do 10 again. Okay, I'm going to make that a bit bigger so I can read it. So we've got 8 and 7 is 15, add 4 is 19. Okay, so we'll put 19 in there. Okay, we'll press 10 again, get 50 rolls. Just need to make it bigger. So we've got 9 and 10 is 19. Add the 6 is 25. Let's put 25 in here. And then we do another 10 rolls. So I've got 12 1s, 10 3s, that's 22. I can't read that one, is it? 9. So we had 12 and 10 is 22. Add 9 is 31. And then if we do 70 rolls, okay, we've got 12, add 12, add 9 again, so that's 24 and 9 is 33. A couple more to go, so let's get 80 rolls. So let's make that bigger. We've got 13 and 14 is 27, plus 10 is 37. And another 10, we've got 14 and 15, which is 29, plus 11 is 40. And then we've got 17 and 17, which is 34. Add this one is 46. Okay. If you want to have a go at this on your own, you can just load that simulator again. It was on last lesson's Show My Homework. Okay, so interestingly enough, it's going to you might have spotted with the numbers what's going to happen. So I can get this back. There we go. So we're going to work out relative frequencies. So actually the first one, 5 out of 10, relative frequency is going to be 0.5. That's what we would expect. We'd expect half of the numbers to be odd, so that's coming out quite nicely. 11 out of 21. Okay, so 11 out of 20 is 0.55. Okay, 16 out of 30. Type that in. We get 0.533. It'd be good if you just pause now and fill the rest of those in. Calculate them on your calculator. So this is your total number of trials, this is your frequency, you should be able to fill those in. What we're going to do next is we're going to plot these points, okay? So actually, what often happens is we start with numbers that are not 0.5 and get close to 0.5, whereas we've started here exactly on 0.5, but that's experiments, they don't always go as you expect, but this is come out at 0.5. So when I did 10, that's here, that would be my first point here, 0.5. My next one is 0.55, and that's at 20. So this is 0.5, this is 0.6, so 0.55 is between the two. Then I've got 0.533 for 30. So there's 0.5, 0.55, 0.33 is just slightly lower. There, okay? So pause, complete the rest, and then we'll come back and finish this graph off. Okay, so these are the results in the table so far. I actually took it a little bit further. So we started off quite nicely. We were close to, well, we had exactly 0.5, which is what we'd expect. We'd expect half of them to be odd. And then we went a little bit higher, and then down and back to 0.5 again, back up again. But then we seemed to be getting lower and lower and lower here, which was not worrying, but it was just unusual. So I did go do a few more just to see what would happen. And it went lower again, but then you can see it started coming back up. And if we did a few more, I think what would probably happen is it would come back up, go above 0.5, and so on. So what you can see on the graph, these are all the points that we've plotted, all the relative frequencies. So we started off at 0.5, but like I say, we went a little bit above, then we came a little bit below, then we went up again, and then we came really quite low, unusually. But you can see we're making our way back up to 0.5. So 0.5 is what we'd expect. We'd expect the probability of an odd number to be about 0.5, but in experiments we never get that exactly. But what you can see is we are close to 0.5. And the more experiments we did, the more we would still be slightly up, slightly down, but we get closer and closer to that line. Okay, this bit's unusual, but that's what happens with experiments. Okay, so again, if you would like to have a go at that on your own, then use that simulator again. You could just Google dice roll simulation. I'm sure you'd find it, but it is on Show My Homework. Okay, I will see you next lesson. Okay, bye-bye.